So I will be covering the rest of my presentation, that is agriculture, structural integrity and ground subsidence in my first presentation, and in second part I will be covering the snow cover. So I have selected 8 or 9 case studies which I have done recently for this presentation. And before that, I will start with the basic thing, that is what is remote sensing and what type of sensors that we use. So I hope that everyone is from remote sensing background here. So just a brief introduction. Remote sensing is nothing but science of capturing different information using some sensors which are mounted at different platforms. So without coming into contact of any of the um, object, we can collect the information about that, and that is remote sensing. Here, two things are important: the source of energy and the platform that we are using. The source of energy can be sun, that we use for optical remote sensing, or it can be the a part of a sensor also that we use for our microwave remote sensing. So based on that, we have two types of sensor, that is passive sensors and active sensors. Passive sensors are those which work with the energy of sun, and active sensors are those which work by their own source of energy. So most of the optical satellites work as a passive sensor, and active sensors are usually microwave remote sensing sensors. So other forms of active sensors are LiDAR, which are lasers which are mounted in the satellites or uh, any platform like aircraft, or nowadays is even the UAVs, and which can capture the point information about the ground objects. Point information means latitude, longitude and elevations. So this is a usual flow chart that how we do different type of correction. First is that using the electromagnetic energy, we collect the real world data and the sensors. We collect the real world data. Then the 3, 4, 5 says that we have different type of sensors and the platforms. Then we have to radiometrically correct the data and geometrically correct. This is true for both microwave and optical data. Then we can use the images for enhancement. We can enhance the image, or we can perform different type of analysis, and then we can perform classification or any other activity with the images to get the information that we want. So coming to the optical and microwave remote sensing comparison, we have microwave sensors uh, which are we can say have some advantages over optical data. Like in optical data, it is constrained by the fact that the sun has to be available to collect the data in with the help of this sensor, and it does not have the all weather availability like the microwave data. Because what happens that with the cloud, the camera cannot penetrate the cloud and cannot capture the ground surface, but microwave data can pass through the clouds. So microwave data works in any type of weather. Second thing is that sun is not available in the nights, but microwave data are collected through its own energy source, so it can even work at the night time. The same type of images will be visible during the day and the night. The radar waves can also penetrate through soil up to some extent. The depending upon the frequency used, it can penetrate to some extent and can reveal the information about the topsoil. So that is the most advantageous part of the microwave, that it can penetrate the some of the surfaces like dense vegetation cover. Some of the optical data will have clear cut disadvantage over there, that suppose you are studying a soil and you have optical data, then you will only see the top portion of the trees. But using the microwave data, you will be able to, some frequencies you will be able to see what is below those trees, because the trees will allow the microwave radiation to pass through. Similarly, the microwave remote sensing has various wavelength band available, which has different interaction with different features on the ground, and in turn revealing information which are not revealed by the optical remote sensing, such as it is very easy to create subsidence data using the microwave remote sensing, which is hard or next to impossible to generate such data with the optical data. Now coming to the microwave data types and techniques, the usual bands that we use, the microwave data ranges from Ka band to P band. There are Ka band, K band, Q band, X, C, S, L and P. However, in the imaging microwave remote sensing, we use usually X, C, L and P band data, and it has two type of resolution, azimuth resolution and range resolution, and the data is provided to user in several forms, that is raw data, SLC data, MLC data, polarimetric data and interferometric data. SLC and MLC has uh, one has the advantage that it has both type of information, that is uh, about the range and the azimuth, and MLC data has a better resolution and less noise, because several data are looked into one, forming a single complex. It is called multi-look complex. So several the information from the several bands or several look directions are compiled together to form a much clearer and a better resolution data in the MLC data. So both have their advantages and disadvantages. So now coming to the synthetic aperture radar. What is a SAR? We are talking about the microwave remote sensing, and we have different type of data, and the most important term that we use is synthetic aperture radar. Microwave needs to collect the information from a microwave, we need a radar. A radar is a device which can emit the microwave signal and get it back. But in satellites, we cannot send a very large radars. So there is a disadvantage in the resolution of the data, because as large as the radar will be, the resolution will be much higher. So with a small radar, we can get a very coarse resolution. So what we do is that we utilize the movement of the satellite and synthetically creates a large, uh, a very large radar. So this is called synthetic aperture radar. So it is not the actual aperture of the radar, but the aperture is created synthetically. Like in point 4, you can see, to overcome this limitation, the SAR capitalizes on the motion of the spacecraft to enumerate a large antenna about 4 kilometer for a ERS SAR data from a small antenna which is only 10 meters. From a 10 meter of radar, we create a synthetic radar which can simulate like a 4 kilometer of a size of the radar. Now coming to the polarimetric data, here the figure and there are two type of polarization which usually we can find in the radar, that is HH and VV polarization. Then there are cross polarization HV and VH. That what does it means? HH polarization means the radar is sending the signal in horizontal polarization and receiving the signal in horizontal polarization. And HV data means the radar is sending the data, the microwave signal in horizontal but receiving the data in vertical polarization. And similarly for VV and VH. So this has a clear-cut advantages in identification of the ground object, because what happens sometime that after interaction of the radar signals with the ground object, the polarization of the ground of the radar signal changes. So depending upon the property of the ground object, the backscattered signal changes, they may change or may not change their polarization. So if it changes from horizontal to vertical, then HV data will be much useful to identify those type of feature. So now some of the commercial satellites give you the data in all the four HS, VV, VV and VH polarization. So using all the four data combinedly, you will be able to identify each and every type of ground feature much more accurately than with a single polarized data. So coming to the SAR interferometry, it is nothing but the technique utilizes more than one satellite data. Some of you might be aware with the optical term that we use most oftenly, that is photogrammetry. In photogrammetry, what we do is we use multiple optical data for creating a high resolution digital elevation model of the Earth's surface. Similarly, in interferometry, the acquisition from the same radar at different time or different acquisition from different satellites are used together to find out the elevation or any deformation information, or you can collect the geometric information of the ground like topography, deformation due to volcanoes, earthquake and ice field, glacier flows, ocean current and vegetation property. So here we use multiple data, not a single data. Like there is a satellite, TerraSAR-X. TerraSAR-X has several constellation of satellites. One satellite passes and the next satellite pass over the same region after some time. So they collect the data for same region, same area multiple times. So when those multiple data are used to find out the information of topography, then that technique is called SAR interferometry. Then there is another term which is used nowadays much more commonly, that is persistent scatter SAR interferometry, PS INSAR. INSAR is interferometric SAR and PS INSAR means persistent scatter. So permanent scatters like build-up area, that is roads, buildings, act as a permanent or persistent scatter of emitted microwave radiation by SAR remote sensor. So these ground features are fixed at a particular location and they reflect more. So and usually they do not change their position. So this type of persistent scatter they are called permanent features which scatter the microwave signal. These features show high value of coherence, close to 1, and it is because of this that helps in identification of build-up feature from other features, showing a mix of double bounce or volumetric scattering like in case of vegetation. Differential SAR interferometry (DINSAR), when applied to monitor subsidence and deformation that occur in this permanent scatterer is termed as persistent SAR scatterer SAR interferometry or PS-INSAR. PS-INSAR helps in monitoring and mapping of surface subsidence of the urban area Remember, it only helps in measuring the surface subsidence in the urban setting, not any setting, occurring due to variety of reasons like seismic or groundwater. We are exploiting the groundwater, so these case studies will be coming one by one. So coming to the application part of the SAR microwave remote sensing, let us start with the case study 1, that is urban subsidence mapping of the Chandigarh Tri-City area. So this is the Tri-City area of the map. Uh, can you mute your microphones during the presentation? Thank you. So case study 1 is the urban subsidence mapping of Chandigarh Tri-City area. So Chandigarh Tri-City area is one of the most developed region of the country. We can say it is one of the most planned city, but even whatever planning we do, we never plan for the groundwater. So with time, what happened in this area, that lot of groundwater exploitation happened, which has led to the decrease in the groundwater of this area, and it is continuously decreasing. So groundwater when present in an aquifer act as a source of support to the surface which is lying above it. So when the groundwater is removed, what happens? The surface subsides slowly, and sometimes it subsides at a continuous rate all over the area, and sometimes there is a differential settlement, that in one area you will see higher amount of subsidence, and in one area you will see lower amount of subsidence. Why it is important to study this type of subsidence? Because when we build a building, then it the we what is the basic thing that we do before building any high rise building? We lay a foundation. It helps in protecting the building from sinking in the ground. So what will happen if we have built a foundation and we remove the support below it? That means a ground below it. Two of the pillars have the support and two of the pillar doesn't have the support due to subsidence. The building will be in danger. The building will eventually collapse. So the study of subsidence is very much important, especially in the urban region where we have lot of buildings. And when there is a differential settlement, these buildings have a chance of cracking down. So land subsidence is usually defined as a loss in elevation of the surface as compared to the surrounding. This is mainly a downward movement of land surface feature where little or no horizontal movement come into play. During the volcanism or earthquake, there will be some horizontal movement of the surface also, or a landslide. But in subsidence, there will be no horizontal movement of the surface, only the vertical movement of the surface. So subsidence is one of the most diverse form of ground failure which depend upon the loss in piezometric pressure, loss in the underground aquifer, that is caused as a result of over exploitation of groundwater or less rainfall over an area. Suppose the capacity of an aquifer is 1000 liters, and we are removing every year 500 liter, and with the rainfall the groundwater is also recharging 500 liter, then the water will be balanced. But we suppose we are removing 500 liters and it is only recharging 300 liters, then there will be a gap which will be left in the surface. Of the various techniques used world over, DINSAR, that is differential interferometric synthetic aperture radar technique, has proved to be most versatile and robust for land subsidence and deformation mapping. Since Chandigarh happens to be one of the few planned city in India and major urban center of northern India, it become important to ensure the safety for ensure a safe and healthy living environment for the millions of population it supports. With groundwater being a major source of water for all domestic and nearby industry set up in Panchkula and a drastic decrease in rainfall over the year, there is a acute pressure on groundwater aquifers. This is leading to continuous lowering of groundwater table and loss in barometric pressure, which is leading to the subsidence of land features. So one of the study concluded that in Punjab and in northern India, like Delhi and other places, Haryana, Ambala, these areas are seeing a decrease of 1 to 2 meter of groundwater every year. So this is creating a immense pressure on the groundwater. So this is the methodology that we used. We use time series Sentinel-1 data, then some pre-processing is done, interferogram is generated, coherence is studies. This is a common flow chart for all type of studies. So I will tell this once only. I will pass it for the next study. Then phase unwrapping is done, then displacement map is created. This displacement map is vertical displacement maps, and the results of the this study is the subsidence image. So this study has been done using the persistent scatter method, and you can see all these pixels, the blue dots, these are the dots, and this give you the amount of subsidence in this area. So although the Chandigarh is showing a similar amount of subsidence, but this region, uh, let me select a pointer. Yeah, but this region is showing a high amount of subsidence, and this is the air Chandigarh
Hello,
airport.
sir. Hello.
Yes.
Sir, your screen is showing the presentation if you are showing something else.
Yeah, it is showing the presentation itself. Can you see the pointer?
Uh,
It is over the industrial area written, or in the side bar,
Hello,
which
Dr. Veet.
so the methodology slide is open right now.
methodology.
Yeah, now it's okay.
Okay, okay. So there must be some delay due to internet. So this is the subsidence map of the Chandigarh Tri-City area, which we have prepared using the data of 1st January 2018 to 1st January 2019. So 1 year period was selected, and we can see that lot of area is showing high amount of subsidence. So this is the unit here is mm. So 16 mm, 17 mm subsidence we are observing in most of the area, 15 between 15 to 16 17 mm of subsidence. So this is a high amount of subsidence. If we the unit is mm, means 1 centimeter in a year. So you may feel that this is a very less amount, but with a continuous period of this type of subsidence, it is a very high amount of subsidence, and it is very dangerous for the building. We have even done some field study in uh, this area. That picture is not included here, but we clearly see that the buildings are already showing the signs of damages, and some building or many building in the airport area and in the Panchkula area are showing that they are cracking. Some of the walls are showing that it has cracked. Why a particular wall is cracking? Because that area is differentially settling. One area is not settling that much, another area is settling. So the crack will be developed in the wall. So same study was done over the Rudrapur city of the Uttarakhand. It is near Nainital, and this also showed the 1.9 centimeter of subsidence every year. So coming to the case study 2, mapping of deflection caused due to hydrostatic pressure variation using the de-Insar method. So what is the hydrostatic pressure? So when we build a dam walls are built to be a rigid body. If you will ask any civil engineering person or to be specific structural engineering person, what he will respond? That dam wall cannot move because they are very rigid body. But that is not true. When the reservoir fills, it exerts lot of pressure into the dam wall. If we take the example of Bhakra dam, which is one of the largest dam in India, once it was largest dam in Asia. So it has a reservoir around 100 kilometer long, and that reservoir is around 2 kilometer to 3 kilometer of width. So millions of gallons of water is uh, stored in that reservoir. When that reservoir is completely filled, that will definitely exert more pressure to the walls of the dam. So, a way, and to monitor the movement of the wall, if you will go have the privilege to visit any dam from inside, you will see that they install a plum type of arrangement inside the dam, which moves with the deflection in the wall of the dams. So they also monitor the deflections very closely, because if the deflection is more than a certain threshold value, they can cause cracks in the walls of the dam. And if you know that if a dam breaks, then what will happen? It will be a catastrophic event for the people living in the downstreams. So suppose Bhakra dam breaks, what will happen? Almost every place in Punjab will be destroyed up to Delhi. So most of the place will be filled with water, because you can imagine 100 kilometers of dam with a depth of 200 to 300 meters and 2 kilometer, 3 kilometer width of the dam. So lot of water is present there. So the technique involved in this study is differential SAR interferometry. So DINSAR involve a repeat pass configuration of SAR interferometry with minimum baseline. Minimum baseline means the distance between one satellite and the other satellite. The central point of one satellite and the central point of the other satellite. The presence of any random motion on the surface or surface feature on the earth tend to decorrelate the backscatter signal and add noise to the phase difference. There are two type of thing we need to understand here when studying a microwave data. One is backscattered signal, one is phase signal. So these two information are present in any of the microwave or the SAR images. So backscatter is the amount of amount of energy which is reflected back by the satellite. And what is the phase difference? Anyone has idea? Let us make the talk a little bit interactive so that it doesn't become too boring. So anyone have the idea about the phase? What is the phase of a electromagnetic hello? We electromagnetic radiation when captured through satellites. Okay, so phase is the information about the time taken to travel by the satellite. It is not the exact definition, it is the broader definition. So with let me try one thing. So phase contains the information that how much time does the satellite took to come to the earth and return to the signal. If you can see this diagram, this is the wave propagation. So this is one, this is one wave. So if the satellite is releasing the wave from here and it is covering coming up to here, then one wavelength we can say that this is the wavelength. So we can measure the wavelength where it is coming back to the satellite. So if the satellite is receiving the wave here, so we can say that it is receiving one third of the wavelength, and then there will be total full number of wavelengths. So uh, say from satellite to earth there is 1,000 full cycle of wavelength and some, some partial wavelength. So suppose one half wavelength and the wavelength is measured in meters. So 1,000, and suppose the wavelength that we used is 10 meters. So 1,000 into 10, so 10,000 meters, and the half wavelength 10,000 point half wavelength means 5 meters. So 10,000 and plus 5, 10,000 5 meters. Okay, so that will be the total phase of that signal. And if there is any change in this phase, suppose there is a building and the satellite is taking the measurement over that building, repeated measurements. So in one measurement we measure the distance as 10,005 meters. In another measurement we take that reading as 10,004 meters. So there is a difference of 1 meter. So what is that? Why that difference has been there? Because of the movement of that particular place. That place could have moved 1 meter below due to subsidence or any other thing. So coming to back to this study, this study aims to measure the deflection that has come over a period of 1 year on the wall of Bhakra Dam, that is in Himachal Pradesh in India, due to change in water level and the pressure exerted by it. Using DINSAR, the deflection was measured to be around 0.952 centimeter, 0.95. So 9 mm of movement from August 2017 and October 2017. Why we selected this time frame? Uh, we selected this time frame because in the end of August, what happened that the dam was almost empty. Starting of the August, dam was almost half of the level, and in August 2017 there was a huge rainfall in the upper reaches, the catchment of the Bhakra. So the dam was filled very quickly. So if the dam is filled very quickly, then there will be a high amount of increase in the pressure in the dam wall, which will cause deflection in the wall. So this picture that you are seeing is of Bhakra Dam. So this is the dam wall, and we observed if there is any movement in this dam wall. Why this type of study is very important? Because I will tell you one more thing. I told you that the different plumb type of arrangement is installed inside the dam when they are built. With time, what happened that these plumbs stop working. So now they don't have any uh, instrument in the dam to measure these deflections. So using the DINSAR or persistent scatter SAR interferometry, we can we will be able to monitor the deflections caused in the dam walls. So this is a demonstration study which we did and check the capability of the Sentinel data. So using this data, we were able to map the deflection at the dam wall of around 0.952 centimeters, 0.9 mm during this period.
Sir,
Yes,
sir, I have a question.
yes, please.
Sir, this phase from this you showed that how can we measure the subsidence in different structures.
Mm-hmm.
So, sir, can we also measure the upliftment in case of some natural phenomena in case of mountains rising or some place rising using the range the phase only?
Yes, definitely. Whatever the phase change is there, we don't study only deflection. We study the phase change. Phase change means how the surface has moved. It may be downward movement. It may be the upward movement. So any of those type of movement can be studied using this type of data, interferometry technique.
Okay, sir. Thank you.
But it has to be sufficient enough, like in some then only you will be able to use that information to um, this data to get that information. Okay.
Yes, sir.
So now coming to the case study 3, that is the C-band SAR interferometry based flood inundation mapping. So in this study, we utilized not only the phase information but also the coherence information. Coherence is that how the reflectance is changing from one time period to other time period. The back scattering. Suppose there is a dry surface. So the back scattering from dry surface will be higher compared to the back scattering from a wet surface. So, or the coherence will also decrease if there is sudden or large amount of change in the surface type, like in case of landslide. What happens, that rocks are present in a slope, then with a landslide those rocks move, so there is a high difference in the backscattering signal, so the coherence is lost. So if the landslide is small enough to be measured by the satellite, then the coherence, then using the interferometric method, we will be able to measure those. But if the movement is too large, we will not be able to measure those movements. And similarly, in case of water, what happens? Water reflects, absorbs most of the back scattering signals from the microwave satellites. So if water, suppose there is a flood event, then what will happen? The back scattering will decrease. So you can see here in the image that the river and the lake which are present are appearing darker, and the surrounding areas are, some are whitish and some are gray. So if the EC of the surface is high, then the back scattering will be low, and if the EC of the surface is less, then the back scattering will be high. So coming to the study, just a second. Proper mapping of the flood can help to delineate the area with higher loss of life and property, thus adding to the relief measures. So this study aims to analyze and exploit the potential of SAR interferometry for flood inundation mapping using a pair of C-band uh, dual polarized data from Sentinel-1 data. The data sets were pre-processed for speckle removal and radiometric correction Thereafter, subset of the study area was taken and the data set was co-registered, followed by interferometric processing. Co-registration of the data is very much important, because if you don't co-register, then all the coherence will for all the pixel will be lost. So yeah, when we use remote sensing, any technique in the remote sensing, first thing is geometric correction, and geometric corrections include the co-registration of the data. The results show low phase shift in and around the river and to some extent in the urban area, which generally does not happen unless there is an increased single bounce scatter.
Sir,
Uh, yes.
sir, voice is very low, sir. We are not able to listen properly.
Okay. Okay. Now is it okay?
Yeah, sir. Enough. It's fine. Thank you.
Okay. Uh, so coming back, the topographic phase removed interferogram showed high phase variation in the core or of the urban area, while coherence maps show an acute loss of coherence from permanent feature as well, which showed high degree of flood water accumulation. This flood was mapped by masking out the low value of high coherence area from image using a proper threshold value. The high degree of flooding was observed in the urban area, and much of the agricultural land was seen to have been submerged under water once the resulting inundation map was overlaid on the Google Earth. So here a slight change in the methodology. We used time series data, pre-processing was done, interferogram was also prepared, and then which was used for preparing a DEM of the area when there was no flood, and then coherence threshold masking was done to find out the flood inundation map. So here we can see two images, one without flood and with one with flooded portion. So here you can clearly see in this area that lot of water is being present. The blue color represents the water, because see the river, lake, which are common in this image also, but the water level in the river has also increased, and this nearby regions are completely flooded. So after preparation of the coherence map, you can threshold it to give you a binary image. The binary image will contain the flooded area and non-flooded area. First image, master image, is from January 2018, and B is from the September 2018 of the Gorakhpur region. So any more questions from what we have discussed till now?
Sir, I want to confirm with this coherence thing. Sir,
Mm-hmm.
is it the, like, if we are taking two images, then that how much similar they are, would we would say that it is more coherent. But if there is different, then we will say less coherent. Is it so, sir?
Yes. If suppose in first image there is a area, and in second image the area is completely devastated by the earthquake, so you will lose the coherence between the two images, because the
Oh,
ground surface feature has changed substantially. Similarly, this happens in the case of glaciers also, because people have tried using SAR interferometric method for studying the glacier movements. But what happens in the glacier, that in a very short span of time, the movement is very high, and the and the surface also changes, because now there is a snow will melt in next 1 month till the next satellite image comes. So the ground feature is changed, and thus there is a loss in the coherence from one image to another image, and thus this SAR interferometric method usually fails in studying the glacier movement and glacier elevation change method. So now coming to the another important topic, that is uh, study of the soil health parameter using the sentinel data or the SAR data. So, sorry, that we will come later on. And there is a one more study related to flooding. Here also we used this SAR data for mapping of the flood and also estimating the runoff of the area for the Roopnagar area. So what happened last year, that where the IIT is built currently, just a second. Where the IIT is built currently, it is in the banks of Satluj River. So Satluj River is passing from 1 kilometer from the IIT campus, and there was a lot of rainfall in the last season, and which led to flooding of the entire campus and the nearby area. So even the campus has to be vacated for few days. But this is quite common for this type of area. The area which are in the flood plains will, with the high amount of rainfall, this type of things happens. But if you can study and you can map the complete extent of the flood, estimate the volume of water which is filled inside the area, then you can take up some measures to divert that flood into other low lying areas. So here we use the data from 18th August 2019 to estimate the maximum runoff on 18th August 2019 was estimated to be 350 mm, while the average daily rainfall was estimated to 120 mm. The estimated runoff gave high correlation with the rainfall, with the R square statistics of around 0.94 and 0.93 for 6th and 18th August. So here we not only studied the flood, we also studied the runoff. The runoff was studied using the SCSCN method, that is soil conservation service curve number method. So this is one of the most tested method for estimating the runoff or runoff modeling. So here you need DM of the area, you need land use, land cover, and using this to rainfall data, and using these three things you can find out the runoff map. So this was the map which we were able to create, and this area in figure C here, you can see that area is completely
Sir,
covered
the
with.
introduction size slide is visible now.
Okay, now is it? Now is it visible, the map?
Sir, it's showing the same slide, the introduction slide.
Okay, wait for some time. I think it will change.
Now it's changing.
Yeah. So this is the campus of IIT Ropar. So you can see in this image that this campus and the nearby villages were completely filled, and the beauty was that the water didn't come from the Satluj river. It came from a river. If I can show you here, there is a small river which is flowing uh, in this side of the campus, that is called Budki river, and it is a seasonal river. That river breached, and this entire area was flooded. And why this area was flooded, the most funny reason was, to protect this area from the water of Satluj, a lot of bunds were built here in front of the campus, and because of those bunds, the water which breached from the Budki river could not leave that area, and the area this campus was entirely flooded. To remove the flooding, the bunds were cut off, and then we were able to remove the water from the campus. So SAR data is quite useful in creating any flood map, subsidence map, so which is clear now from these 2-3 case studies. These are the field photographs. This is the residential area of IIT Roper, and this is the transit campus. We are currently one campus is running. So this area was completely filled, and the same thing was. So this was this map was also verified in the field. So now coming to the next important topic about SAR remote sensing for soil studies. Is it visible? The slide has changed. Can you confirm, please?
Yes, sir, it is same.
Sir.
Thank you. So soil parameters are something that we need to study using the remote sensing data, because till now what is happening, that all these soil parameters are studied in the field only. So it is 10:33, so we almost completed the part 1, but and we can take up some questions. But what I will do is I will continue with the presentation, and together in the next session, after I finish, we can take up the questions and discussions. Is it fine with everyone? Yeah, so I guess it is fine. So I will continue with the talk till 11, and after half an hour break, when I will start next session, then I will finish up my presentation, and then whatever time is left, we will be continuing with the discussions. So coming to the SAR remote sensing for the soil studies is that soil parameters are usually, you might have heard about the soil health card. Soil health card is prepared by government to indicate the fertility or the health of the soil. The health of the soil depends upon many parameters, like what is the organic carbon content of the soil, what is the pH of the soil, what is the electrical conductivity of the soil, what are the chemical components of the soil, like nitrogen, potassium, phosphorus. These are the three major components of the soil which is important for plant growth. Most of the plant growths: nitrogen, phosphorus and potassium, NPK. So these are the samples from the soil is taken to the laboratory. Samples from the soil is taken to the laboratories, and they are studied. So we have two major problem with this method. One, the time taken for collecting the soil sample is high. It is tedious process, and when we are analyzing the things in the laboratory with the various sophisticated instrumentation and all, it is a costly process. So how much soil samples we can take? We can take very little soil samples. Even till now, we were not able to study the entire Indian soil types, soil health. The government is investing lots of money into that, but we are not able to study all these features. And second thing, these parameters are very dynamic. So one season the potassium content of the soil is something, next year it will change. The organic content of the soil changes every few months. So the these we study a particular field today, and after a month the property of the soil will change. Then another important parameter is soil moisture, because if we know the moisture content of the soil, then we can determine which type of crop it can support, how much irrigation will be required for supporting x number of crop, x type of crop, like wheat and paddy, wheat and rice, which type of crop it will support. Rice need more water, wheat need less water. So if the soil is more moist, we can put rice into that. If the soil is less moist, irrigation is not available, then it is suitable for wheat growth or corn growth. Similarly, and these parameters are very, very dynamic. So even if we have the facility of studying all these things using the laboratory, then also imagine the number of samples that has to be studied and how frequent that has to be studied, and this testing takes lot of time. So studying, we have to find alternative to study these parameters, at least those parameters which has a direct relationship with the satellite data, the backscattering in case of microwave and reflectance in case of optical data. So optical data is very good for studying soil moisture and even the organic carbon content and other features. But microwave data has been very proved to be very useful in studying the soil moisture, because I said that backscattering will depend upon the electrical conductivity. Electrical conductivity will depend upon the soil moisture and type of the soil. So ultimately soil moisture will lead to uh, change in the backscattering of the SAR signals from the satellite. So in principle microwave data can be used for studying the soil moisture. Till now there has been a lot of studies using the and microwave satellite data for studying the soil moisture and electrical conductivity and other features. But all those studies are very complicated in terms of data and in terms of processing. So our main goal was to simplify those data processing steps and also to reduce the cost of data processing. So how we can reduce the cost? We can reduce the cost by using the freely available data and not using the commercial satellites, because commercial satellite, everyone knows that they are very high resolution and they are very good in giving this soil moisture and other electrical conductivity and other parameters for the soil health. But the sentinel data which is available free of cost was not that much exploited for studying the soil moisture using a simple method. Even if it was done using the sentinel data, the methods were very complicated. The another advantage of using the remote sensing data for this soil study is that the sampling method that we use to do for laboratory testing, how many samples we can collect for a village or for a plot? We can collect one sample of a plot, or say 5-10 samples from a village. So not all the fields can be studied, and these parameters are dynamic. Even in the same village, the particular one plot can be saline, another plot cannot be saline. One plot is having good amount of moisture, another agricultural field will have less amount of moisture, because the soil type changes, the irrigation pattern and many other factors are playing into role. So by using the microwave remote sensing data, we get a continuous data. So for every 20 meter we are getting one value. So it has clear cut advantage over the laboratory testing method. So here these are the soil health parameters like soil moisture, soil nitrogen content, soil salinity and soil organic carbon content. These are the important parameters that we are trying to measure using the remote sensing microwave data. Soil nitrogen content, it is still under investigation, because nitrogen content is a very dynamic parameter and it changes over overnight also. uh, Suppose today I put some fertilizer, the nitrogen content will increase, the next very day it may decrease. So the case study 5, that is synergistic utilization of Sentinel-1 SAR and Sentinel-2 optical remote sensing data for surface soil moisture estimation over the Roopnagar, Punjab, India. This paper has recently been published in Geocato International. So this study utilizes Sentinel-1A C-band SAR remote sensing data with VV and VH polarization channel for surface soil moisture estimation for alluvial soil and its subtype in Roopnagar of Punjab state in India. While index-based uh, OLS, that is ordinary least square regression method for soil moisture estimation, was done using backscatter from the Sentinel-1 SAR data. It was validated using normalized difference moisture index NDMI generated from Sentinel-2 optical data. So I said that optical data are very much tried and tested for estimating this uh, soil moisture. Then also we are trying to develop new methods. Why? Because optical data has limitation of coverage during the rainy seasons and during the cloudy season, or in the fog they will not give you the correct measurements. But microwave data are having the capability of working in every type of season or every type of weather condition. So if we can use the microwave data with the same accuracy that we can use the optical data, then it is well enough to be used as an alternative. So this approach, though did not consider the actual soil moisture data from the field, yet gave a low root mean square error. We are talking about a unsupervised approach. There we used the ordinary least square regression and the backscatter from the SAR data only. No field data was taken here, and the accuracy that we achieved, the R square statistics of this study was around 0.72 in the training and testing phase. The index-based ordinary least square regression method for soil moisture estimation aims to establish a technique for cases when field data is either not available or the study area is not easily accessible. In the second method that we use is that we use the field data also, and the accuracy here increased from 0.72, that is 72%, to 0.96 percent in the training phase, and in testing 0.94 method. 94% in accuracy was established using the field data. So we went to the field, collected the data first to establish a relationship between the backscattering and the moisture content, and then that data was the backscattering was used to predict for the not predict, estimate for a time period where we had some of the field data available, and the field data was only 1020 field data, and we estimated for entire Roopnagar area, and the accuracy that we achieved was around 94% with a confidence level of 97.5%. So we can say that this result was too good. And here we use only ordinary least square regression method and nothing else, not a complicated model for estimating. So it can, the processing time and cost is also simple. The method can be used by everyone. The main problem why microwave is not very popular is when you will read the papers by various groups in microwave, it will be so complicated, so much mathematics will be there, so much things will be there, that at last what a student will do, it he will read the paper and then he will say it is something of different level, we will not be able to do this. Because people don't give everything in the paper, and they give unnecessary equations and a very large model where the computational power requirement is too much. So we developed a very simple regression method, and we achieved the accuracy better than those methods using free data. So these are the moisture trend uh, which were collected from the soil field, and here you can see that we have collected the moisture from various depths, from surface to up to 60 centimeter of the depth, because our aim was not only to estimate the surface soil moisture, which is usually done by most of the remote sensing method, because whatever reflectance is there, it is there from the topsoil. So we get the moisture content of the surface. But where are the roots of the plants? The plant roots are usually below surface. Sometimes it ranges from 40 centimeter up to say 150 centimeter or 200 centimeters. So for various plants the root zone is different, and whatever the condition may be at surface, the surface may be moist, but the moisture content at the zone uh, determines the capability of plant to grow in that particular soil. So these are the field data, and these are the NDMI map for the Punjab for various months, which was used for estimating the value for the next month. The model was trained using these data, and then it was used to calculate the soil moisture using the backscatter of the Sentinel-1 data. So this plot shows the correlation between the surface soil moisture from the field and SAR backscatter in dB for VH polarization and BB polarization. So here you can see that the correlation R square is around 9.4, and in case of VB it is 9.3. So with the VH polarization there is a slight increase in the accuracy than in comparison to VB polarization. So this is the goodness of fit and the statistics of